Good day and welcome back to part 5 of our discussion on triple integrals. In this video we're going to focus on two problems that really focus on visualization. So in the first problem we're simply going to sit up, we don't need to evaluate, a triple integral that calculates the volume of the solid bounded by the cylinder y equals x squared and the planes z equals 0, z equals 4, and y equals 9. And what I would like you to do is to pause the video and see if you can come up with your rough sketch of what this solid will look like. So assuming that you have paused the video and came up with your rough sketch of this solid, let's go ahead and work through it together. My intuition when I look at this is the z equals 0 and z equals 4 are going to bound our solid above and below. The y equals 9 is going to bound it on the right, and y equals x squared will bound it on the left. So let's begin with y equals x squared. When I go to sketch this cylinder, I pick the simplest trace to work in. That would be the z equals 0, i.e. the xy plane. So in the xy plane, we simply have this parabola, y equals x squared. Now note this parabola opens up indefinitely along that positive y-axis, but it's capped off on the right by a value of y equals 9. So I'm going to mark off 9, but also remember this cylinder extends indefinitely upward and downward along that z-axis, but it's capped off below by the xy plane and above by the value of z equals 4. So if I indicate z equals 4, that would be the top part of the solid, and we are in the cylinder above z equals 0, and we're capped off on the right by y equals 9. And just to make sure we all see the individual surfaces, the right-hand side is y equals 9. The top is given by z equals 4. The bottom is z equals 0, and the left is made up of the cylinder, y equals x squared. Now that we have a visualization, what we would like to think about is setting up a triple integral. This is one of those examples where we can set up the triple integral for the volume in multiple ways. Let's give ourselves a starting point. The volume of the solid E would be the triple integral over E of the function 1. And recall with a triple integral, our generic template is an outside double integral and an inside single integral. And how we determine the variable of integration on the inside is we think in what direction are we viewing this solid as varying in. And to me, I see immediately it looks as though it's varying very nicely in the z direction, where we're varying from z equals 0 up till we hit z equals 4. So if we put z on the inside from 0 to 4, then we'll just have one more step. We need to turn this outside double integral into an iterated integral. And once we have this completely set up in terms of limits of integration in a desired order, that would be the setup of the problem. To see the region of integration for that outside double integral, recall how we would like to view this. We want to think if we were to take our solid and compact it down into the xy plane, what would we be left with? And we see this parabolic type region. And I'm going to sketch this in a separate xy coordinate system. And it looks as though we are going to have this parabola now, y equals x squared, but we cap it off at the top by that value of y is equal to 9. So note, x squared equals 9 when x is equal to plus or minus 3. And for an x value of your choice between minus 3 and 3, those corresponding y values vary along vertical lines from the smaller value y equals x squared to the upper value of y equals 9. And we just described precisely our limits of integration. So x on the outside, we have numbers from -3 to 3, and y for such an x value varies between x squared and 9. And just to give us maybe the best possible visualization, let me go ahead and add a video of a GeoGebra file. So in this video, we can see in red the cylinder y equals x squared. Then we're adding in z equals 4, the top, y equals 9, the right. And we can see in between here our solid. Let's make this a bit more clear. If we get rid of some of these extraneous portions, we have our following solid. And what I would like to do is rotate it around so we can now see that when we're looking at it from above, so the z-axis is coming straight out of the screen at us. This is the bird's eye view from above, which is exactly that region of integration for the outside double integral. We have y equals x squared, and it's capped off above by y equals 9. But then we also take a moment to point out this isn't the only way to view it. We thought of the surface as varying in the z direction. What if we thought about it varying in a different direction? So notice when we look at it along that y-axis, so now if we think about it varying in the y direction, when you compact it down into the xz plane, so note the positive x-axis to the left, positive z-axis above, what you end up with is a very nice rectangular region. So while we are at it, let's go ahead and set this up a different way as well. So we viewed our surface as varying in that z direction, but as we just indicated in our GeoGebra video, we could easily think of this as varying in the y direction as well. So if we're varying this in the y direction, our basic setup is going to be that the volume of E is a double integral on the outside, a single integral in the y direction. And we have to think, how do we vary? Well, in the y direction, you vary from the smaller surface, y equals x squared, and then we vary in that y direction until we hit that end cap of y equals 9. So the inside limitations in terms of y would be going from y equals x squared to y equals 9. For the outside double integral, we play the same game again. We think if we take our solid and we compact it down into the xz plane, what do we have? And it's exactly that rectangle that we witnessed in the GeoGebra video. And note that rectangle is such that it's bounded above by z equals 4. Note we're in the zx plane. And as we saw, the x values vary from -3 to 3 because those x values of -3 and 3 correspond to when y is equal to 9. And now we just need to think about how we want to set up our limits of integration for this outside double integral. And either or will work, of course, because it's a rectangle. So let's kind of just arbitrarily just say dx dz. In the middle, the x values are from -3 to 3, and on the outside, the z values vary from 0 to 4. And if you were to evaluate either one of these double integrals, you would get back the same value representing the volume, and that number that you would get back, because I know you all want to practice, is 144. Let's now move on to a second highly visual example. And this is very similar to something we saw in a previous video, the idea being that the triple integral represents a volume of a solid, and we would simply like to sketch that solid. And remember, because we are integrating one, whatever these limits of integration correspond to, that would be our solid. So let's break this down into parts. We think of this as an outside double integral and an inside single integral. And for that outside double integral, let's sketch what that region D will look like, and then we will take D and bring it into the three-dimensional space. So D is described by having the x values vary from 0 to 1, and then the corresponding z values varying from 0 to 1 minus x. So z equals 1 minus x in the xz plane would be a line having z-intercept 1 and slope minus x. And what we are told is that for a value of x between 0 and 1, the z values vary along these vertical lines going from z equals 0 to z equals 1 minus x. And we can see this triangular region in the xyz coordinate system. So note in the xyz coordinate system, we have this triangular region, one in the z direction, one in the x direction, so that this triangular region represents this outside region of integration for the double integral. What we need to do now is think if we pick any point we want in D, how do the corresponding y values vary? And the observation to make is that the y values vary from 0 to 2 minus 2z. Note that y equals 0 puts us in this xz plane, and we're bounded above by y equals 2 minus 2z, where y equals 2 minus 2z is really a plane. And in terms of visualizing the plane, because the x variable is not present, we might want to think about that x equals 0 trace. That is, flat in the screen in the yz axes, we have a line that crosses the z-axis at 1 and the y-axis at 2. So 2, and in red I'm representing the plane y equals 2 minus 2z. And note this is once again just the x equals 0 trace. If you really want to think about what that plane y equals 2 minus 2z would look like, you would drag this red line in the direction kind of parallel to the x-axis. And what we need to do now is for each point in D, this triangular region to the left, we need to let our y value vary from 0 to the plane. So if you were to start up at this upper point at 0, 0, 1, you're on both planes at once, you can just stay there. But note, if you're all the way down where x is 1 and y and z are 0, you would go in the y direction all the way until you hit that red plane. Similarly, if you were to pick another point on the hypotenuse of that triangle, you would go over until you hit the plane. And note there's a line somewhere in here which is the line of intersection between the blue plane, which is coming from z equals 1 minus x, and the red plane, y equals 2 minus 2z. And if we now get rid of maybe just this extraneous line segment, we can more clearly see our solid. It's going to be bounded on the left and behind by the x, z, and zy coordinate planes, respectively. It's bounded in the front by this blue plane, z equals 1 minus x, and on the right by this red plane, 2 minus 2z. And once again, I realize the visualization here is rather tough. These are certainly not easy problems, they require practice. So let me show you one more quick GeoGebra video that hopefully illustrates this even more clearly. In this video, we have on the left that triangular region D we are interested in, and on the right we have the line segment I previously had drawn in red. This is representing that plane y equals 2 minus 2z. So letting things play, and what we see in blue is this plane y equals 2 minus 2z. And then I'm going to sketch also in here this left or front plane, which is given by z equals 1 minus x. And I would like to think about where those two planes intersect each other. And note this line of intersection is precisely the line of intersection that we drew a few minutes ago. So let's try to clear this out a little bit. We're going to get rid of the two planes. And now I'm going to think, how can I go from this frame to the actual surface? And I've indicated a few points, but remember we have to start off with a point in D, and we vary from y equals 0 until we hit that right plane. So let's draw those in. And then go ahead and now add the frame of our surface. Hopefully that helps to illustrate the thought process and the intuition one would go through or utilize to sketch one of these solids. So in our next video, we'll look at one additional example involving triple integrals that will hopefully set the stage for our next topic. So stay tuned and take care.